Andreas. Thanks for coming, everyone. So I'm really excited to present today's speaker, Oskar. Oskar was my PhD advisor, so it's extra special. And he graduated from UBC sometime in the early 90s. 94? Okay. He at Caltech as a graduate student developed the first crystal lasers, then went to industry for a little while, a startup, came back to Caltech as a professor of applied physics in the applied physics department, and started a group there that initially working on a number of topics, including crystals and optics. And when I joined the group, the new thing was optomechanics. And so bringing in mechanical resonators, and the journey from there, it's extended into a number of directions. These days, one of those directions is microwave frequency superconducting circuits, which we're gonna hear about today. Oskar has been awarded a very large number of awards, including, I guess, the Humboldt Fellowship and various other fellowships. I won't go through all of them. And currently, he's also the head of, in addition to being a professor at Caltech, he's the head of quantum hardware at Amazon on their quantum computing application. So yeah, it's
well, thank you, Amir. It's really nice to be here. I'm glad I made it. We had some really heavy rainfall in LA, so I didn't know if I was going to make it yesterday. But it's really nice to be here, and it's a really nice sunny day. So pleasure to come in and see a lot of friendly faces and get to talk to you today about some of the recent work that my research group has been doing at Caltech on superconducting quantum circuits. So as Amir mentioned, right now I'm on sabbatical from Caltech, and I'm leading an effort at Amazon Web Services to develop gate-based quantum computers using superconducting quantum circuits. But today I'm going to tell you about some work that's more appropriate to quantum simulation. So still using these superconducting quantum circuits. So there's a lot of different platforms that people are using these days. Many of you are experts in these areas to develop what I'll call, synthetic quantum systems. So these are moving from, the control of atoms and photons to, at the individual scale to, larger systems that have many quantum degrees of freedom. And these sorts of systems, many have various different physical incarnations. So there's been a tremendous amount of work for many decades on ultra-cooled atoms, but one can think of those as synthetic quantum systems with many degrees of freedom. There's also trapped ions. In the solid state, one has gated quantum dots. So this is a particularly promising technology for quantum computing. There's also defects in solids like color centers that can form in, for instance, diamond, and these sorts of the electronic states and the nuclear states in those systems can be used to prepare large-scale synthetic quantum systems. And there's also work with photons and single photon detectors, and those can be used to generate, again, large-scale many-body quantum systems. And then finally, there's the work that the area that I'm going to talk about, which are these superconducting quantum circuits. And these are, for those that are not experts, these are microwave systems. They operate at microwave frequencies. You can put them on the surface of a microchip to thin film processing of superconducting materials, and then you include in with them superconducting tunnel barriers, Josephson junctions that add a nonlinearity to the system, and you can create all sorts of large-scale quantum systems. So, and this will be the subject of my talk. But I think maybe as you listen to my talk and think about some of the things I'm talking about, I think one thing that, for me at least, that is still an open question is, we have all of these different physical platforms. We can build now, we can control these quantum systems at large scale. But it's still, I still think that the question is, what sort of really interesting physics can we do? Other than, maybe we can explore new many-body phases. But what is it specifically about these synthetic forms, ones that we can engineer, that really provide benefit? And I don't know if I have an answer. I think it's just fun to do it, and you really, you can combine engineering with quantum physics. But I hope that there's more. I hope that there's really fundamental physics and things that we discover that we couldn't discover without these synthetic systems. And that's, I don't think we've done that yet. But that's, a big part of the motivation for, at least for me and my group. And we still need to develop these systems even further. But I hope to show you, one path towards doing it. Okay. So just a few words about superconducting qubits. I mentioned that these are basically nonlinear microwave oscillators. So we can think of them as nothing more than lumped element inductors and capacitors that form in sort of harmonic oscillator. We can form these again by printing and patterning metal on the surface of a microchip, for instance. And you can form a qubit, it turns out, by replacing this inductor with a tunnel junction, like a Josephson junction, a superconducting Josephson junction. And so this is this circuit development here. And if you do things in the right way and you shunt this tunnel junction with the right amount of capacitance, so the charging energy relative to the tunneling energy is of a specific ratio, then you go from a harmonic oscillator potential with equal, with harmonic levels to something with a cosine length potential and just the right amount of cosine potential that you get enharmonicity. But you're not sensitive. This is in phase here, phase across the junction, but you're not sensitive to other sorts of charge noise. And it's this sort of trans one qubit that is the workhorse of these superconducting quantum circuits. And the so what do these circuits provide? Well, they provide individual qubit control. So single shot qubit readout, fast high fidelity 2-qubit gates. I mentioned that you can print these into two-dimensional circuits of qubit arrays. But typically they involve only nearest neighbor connectivity between qubits. It's not always the case, but typically that is the case. So if one looks at some of the more famous superconducting quantum circuits or processors that have been made, so Google made this Sycamore processor that was designed to implement a two-dimensional surface code. And so you had a two-dimensional array of data and scylla qubits, but all of the interactions were local, right? In this sort of processor. Similarly, you have work at IBM where they have a hexagonal array of qubits, and that has an even lower density of interactions in the two-dimensional array. There is work where you can using cavity mediated interactions, and this was sort of borrowed from ideas that were out there in atomic physics, where people were using optical cavities to mediate all coupling between atoms. A similar phenomenon can be done with these superconducting quantum circuits. This is one of those examples. But these sorts of cavity mediated processes are not fundamentally scalable. And one of the challenges that you run into, especially in these superconducting circuits, is that of frequency crowding. So you start to make your cavity larger, so you can put more qubits in there, and you start to have a multi-moded cavity. You have to worry about not just one single mode that's mediating interactions, but many modes inside of that cavity. And so there's some things you can do to mitigate that, but fundamentally it becomes a challenge to, as you try to scale to very large systems, say thousands of qubits, it's going to be a big challenge to use these cavity mediated processes. So why do we care about that? Well, a lot of the interesting physics that occurs in these many-body systems, especially if you're considering it from a quantum simulator standpoint, is when you have non-local interaction between the particles that are on the lattice. So in the case of trapped ions, one uses photon-mediated interactions with a specific type of interaction power law that you can tailor. And again, that uses the Coulombic interactions and the vibrational modes of the lattices of ions. You also have cavity QED. I already mentioned this. This is work from here at Stanford, where one has arrays of atoms sitting inside of a cavity that provides all-level coupling. But in this work, one can even go beyond that by specifically producing a gradient in the potential for the atoms, and then modulating to directly connect specific atoms together in arbitrary graphs. So that's an example where you have almost full control of the coupling in a quantum system. And then there's very popular work that's being done with Rydberg atoms these days and in quasar arrays. And so here the idea is that you can actually move your atoms around in time and thereby create non-local interactions in time through the physical movement of these atoms. So why do we care about this sort of long-range coupling, and why should we work towards it in superconducting quantum circuit? Well, one, if you're thinking about quantum simulation, it's pretty obvious that the rate at which entanglement can spread and the way it spreads is going to be much more interesting when you have long-range interactions. You can also think of the different novel phases of matter that might arise when you have that extra ability to control that range of coupling. You have many more interesting phases of matter that occur when beyond local interactions. And then you can also use it for computation. So this is not in the realm of quantum simulation, but for quantum computation, there's a fundamental trade-off between the way you implement a circuit, and if you have limited connectivity, then you're going to have an extra overhead to implement certain kinds of circuits, but also in the way you implement quantum error correction. I think this is one of the more important aspects of why one wants long-range controllable interactions inside of a large superconducting quantum circuit, because if you're using it for quantum computation, then you can get a much longer code distance, or you get more logical qubits if you're for a number of physical qubits if you're able to go beyond local interactions, and that's going to be, I think, very important as one starts to develop better and better quantum error inputs. So those are the number of reasons why one would like to go beyond the sort of nearest neighbor superconducting quantum circuit models. So how can we do it? How can we do that in an extensible way? And so one way you can think about doing that is one natural way is to take a waveguide. So let's say a microwave waveguide, which is naturally extensible, right? I can just keep extending that waveguide, and its properties stay the same as I extend it. If I now tether a number of different atoms or qubits along that waveguide, then I can build an extensible quantum system where the waveguide is mediating interactions over some extended range between these qubits. And as I make this, as I just keep extending the structure, the dynamics or the properties of the system shouldn't change. And we did some work looking at that, where we just had a plain waveguide that was mediating interactions between qubits and their radiation field, and you get very interesting types of quantum systems that you do that, but they rely on precise positioning of atoms at special, where that positioning is going to be some fraction of a quarter wavelength, or some multiple of a quarter wavelength of the radiation of the light coming from these quantum emitters. And if you do that, then you can form special types of dark states or bright states. And you can, with the dark states, you can avoid the loss of radiation, and you can form these closed systems that you might be able to use in interesting computations or simulations. But this becomes, rather challenging to always precisely locate these things, and it's somewhat limiting. So maybe, one way of relaxing this requirement of dark states is to actually use not a normal waveguide, but rather to go to some sort of waveguide which has a special type of dispersion in it. So again, we're using the waveguide and the optical states or the microwave states in that waveguide to mediate interactions between our local atoms or qubits. And these are some ideas that were developed by Jeff Kimball and Derek Chang and others around this idea, and they were thinking about how to use the systems for atomic systems, so gas phase atoms in the near field of photonic elements. And they wanted to use the bound states that would emerge in these systems to generate longer range interactions between atoms that were in the near field of these photonic structures. And we played the same game in the microwave domain with these superconducting circuits. So we've actually been able to make similar dispersion engineered waveguides that have topological behavior, for instance. And in this work, I'm going to talk about how we've used these sorts of metamaterial waveguides to generate a many-body quantum simulator with long-range interaction. And fundamentally, this system is extensible, and I think that's one of the one of the most important aspects of it. And it's just got a lot of really cool properties that out there. So how does this how do these systems work? How do I get this long-range interaction between these local atoms on a lattice via this quantum bus that's formed with this waveguide? So it's a very simple process, and the way you can think about it is that if I pattern this waveguide, I get strong dispersion in the frequency versus momentum of that waveguide, so for light, and near these drag points, I will actually open up band gaps in the dispersion, so where light is forbidden to propagate down the waveguide. And it's near these band gaps that one can create interesting bound states that can realize or mediate interactions between the atoms. So if I place an emitter that has a frequency that's just inside this band gap, let's say by delta, then I will form, because it's forbidden to radiate, what happens is that atom actually tries to radiate, this radiation gets reflected, and it binds to the atom, the atomic site, and forms this bound, exponentially decaying wave packet in this case. And the size of this bound state depends on the tuning from this band edge. So the closer you get to the band edge, then the more extended you have your bound state, and the farther you tune from the band edge, the more localized this bound state is. So you have a natural way of creating a bound atom photon state with these sorts of waveguides that can realize this tunable range of interaction via the photonic part of this bound state. And it's naturally protected from from decoherence, unlike these other plane waveguides where radiation can just radiate out into the waveguide. I still have my atom living inside of this band gap, so this bound state does not radiate as long as this waveguide is long. And so then if I have two atoms, for instance, right, then I will have two different bound states. If they're at the same frequency, they can interact, and that interactions can depend on the overlap of these bound states between the two atoms. So by tuning this, by tuning the atom's frequency up to the band edge, I can actually tune the extent of this long-range interaction, sort of flip-flop interaction that we get in excitations of atoms. Well, that's the basic nature of these sorts of systems. As I mentioned, people have tried to realize this. Jeff Kimball and his group and others have tried to realize these sorts of neutral atoms coupled to photonic crystal waveguides. That's a really challenging experiment. Trapping atoms in the near field of these very strong dielectrics is really difficult. And so then the superconducting systems is actually relatively easy. All right, it's very natural to be able to do this. And so there was early work out of Andrew Haug's group where they were doing exactly this. They would make basically a periodic coplanar waveguide, and they'd modulate the impedance of that waveguide. And that modulation would give rise to a very similar sort of modulation like you have in these photonic crystal, dielectric photonic crystal structures, and would form a band gap at a Bragg condition. Again, but these are relatively large structures. It's very hard to fit many periods of these sorts of coplanar waveguides in a single microchip. And so what we looked at is the development of compact metamaterial waveguides. So what are these? These are spiral inductors. So we pattern the aluminum or the superconducting film on top of our microchip. We patterned it into spirals where we want inductors. So tight spirals give you a very large delay length and give you a very large inductance. And then we use interdigitated capacitors to form very small capacitances, very large capacitances in a very small area. And so if you do that, you can form resonances that through these lumped element structures, and you can form transmission lines which have, very similar properties to the dielectric photonic crystal structures that, that I was showing you. And but the beauty is that the waveguide lattice constant, so that the lattice constant of this unit cell is roughly the wavelength over 60, so it's extremely compact. So I can print a very large metamaterial waveguide on, with many unit cells on a reasonably sized microchip, so something on the order of 100 centimeters. And this is just showing you what the theoretical dispersion would look like for a metamaterial waveguide that has this sort of properties, where you have these parallel resonances with a coupling capacitor between them. And in these sorts of structures, you form a band gap region with a passband above and below. And this is just showing you when you realize that, you get a very good correspondence between what you design and what you realize. So this is just showing a transmission measurement through one of these structures where you get very strong extinction in the band gap region. So these are very easy structures to make, to print, basically. And then this allows you to make pretty exotic microwave structures for putting your qubits in. And so this shows the process that I'm going to tell you about today. This metamaterial waveguide quantum simulator that we've made. And so let me just spend a few moments talking about what the structure looks like, or what you're seeing here. So this is a silicon microchip that the gray areas are aluminum. And this is about a few hundred nanometer thick layer of electron beam deposited aluminum that's sitting on top of a silicon wafer. And I'll talk about the pattern in here, but this is the metamaterial waveguide down the center here. So there's each of these is a unit cell, and it has an inductor and a capacitor forming a resonance, and then it has a little capacitive wings that couple each resonator. There's 50 unit cells across this roughly 1 centimeter chip, and then at some of the middle sites, you'll see that we have a few other elements, and these are qubits that are coupled into one of the unit cell resonances of this metamaterial waveguide. And so we have a series of qubits that are loaded. These are transmon qubits that are loaded at these sites. There's 10 of these at the middle 10 sites of this metamaterial waveguide. And then on the output side, these are actually just tapered regions of this metamaterial that allow us to couple to the outside world with 50 ohm transmission line. So we can actually send light through this metamaterial waveguide and collect it on the other side. And then, but embedded inside of this unit cell array are a series of transmon qubits. And each of these transmon qubits has a control line that allows us to excite these transmon qubits, and a flux line, a current line that allows us to tune the frequency of these qubits. So we can move their frequencies relative to any of the band edges of this metamaterial waveguide. This just is a zoom in showing this tapered region. This is just an impedance match between the central metamaterial waveguide and the 50 ohm coplanar waveguide output. This is just a zoom in again of this central region. You can see these are each of the qubits are shown in orange. This is the large shunting capacitance of each of the qubits. And there's 10 of them in the center here. There's also in green here a resonator that is also coupled to this. So each of these qubits is passively coupled into this metamaterial bus, right? And in addition, you have a readout resonator, which is coupled to the qubits, but also coupled to the same metamaterial bus. And what we do is we place these readout resonators, okay, in the passband of this metamaterial waveguide. And that allows us to, when we send microwave signals through this passband, we can actually look at dispersive shifts of each of these resonators, and that will tell us the state of each of the qubits. So we use the passband of the metamaterial to do readout, and then we use the band gaps of the metamaterial, which are at the frequencies above and below the passband. We use that that's where we place the frequencies of the qubits so we can form these downstates. So the metamaterial serves two purposes. One, it acts as a special type of filter that allows us to do readout of all of our qubits. And number two, it protects and forms these downstates for each of the qubits. So the qubits are strongly coupled into this into these metamaterial waveguides, but because they have these band gaps, they don't radiate. They just form these very localized bound states. So the metamaterial waveguide is playing two purposes here. It's acting as a quantum bus to mediate interactions, and it's acting as a multiplex filter for reading out the qubit space. Okay, so this is another optical image of that structure. Now let me talk to you about what sort of physics shows up in these sorts of structures once we start to put excitations into those qubits. So the simplest model one wants to have of this metamaterial waveguide with these qubits that are capacitively loaded into each of the central 10 unit cell sites looks as follows. So let's start with the metamaterial. So to first order in coupling capacitance and self-capacitance, one can model this metamaterial waveguide as a series of coupled with coupling constant J resonant cavities. So light hops from one resonant cavity to the next at some rate J. And again, that's first order in the coupling capacitance, self-capacitance. And so I should expect some sort of, if this is the bare frequency of each of these cavities, omega c, I should expect a dispersion, some sort of sinusoidal dispersion of the frequency versus the wave vector with a range which is 4 times j hopping rate. And so this is the pass band of that metamaterial I mentioned. So this central pass band, it has a bandwidth of 4 times j, and then it has an upper band gap, which I can protect I can put my qubits in there and form bound states, or I can use the lower band gap. So now I add in the qubits, and the qubits are now coupling to each unit cell, so they couple into the cavity at some rate g. Let's assume they're all coupling at the same rate. I get this modified Hamiltonian now. And then if I look at the low energy effective Hamiltonian of this, I get something that looks like an extended Bose-Hubbard model, right? Where I have now on-site potential interactions, and each one of these qubits is anharmonic. So if I try to put 2 excitations on it, I'm going to pick up extra energy. So this is its on-site potential at each one of these sites for photons. And again, we're thinking about these bound state photons, right? These are our particles, so to speak, bound state photons. The qubits are not the particles, the bound state photons are the particles in this case. And then I have tunneling or hopping. This relates to this J. And this tunneling or hopping doesn't just have to be nearest neighbor. It can be beyond nearest neighbor because these bound states can extend over many lattice sites. So this tunneling matrix is not just limited to nearest neighbor because I'm using the bound states, these extended bound states that have overlap over many sites to give rise to this. So this typically the Bose-Hubbard model, these are limited to the nearest neighbor, right? And that's going to affect the quantum dynamics. Okay, so this extended Bose-Hubbard model is one that's been studied a lot in atomic physics. It's also the natural model for circuit QED for superconducting quantum circuits. But what's not natural is this ability to now tune this extended range of interaction through these bound states in the system. So now let's, the first thing we did is we made the circuit, and we wanted to test and then just understand, have we been able to realize this Hamiltonian? Have we been able to realize this sort of system? And so you can go in and you can measure each individual qubit. You can understand its frequency. You can understand its anharmonicity. So that's relatively straightforward. We have individual control of every single qubit. We can read up every single qubit. But then we want to understand the interaction. We understand the talking. So let me walk you through how we do that. So what we do is we take 8 qubits and we park them all the way. And we take just 2 qubits and we isolate the 2 qubit system. We excite one of the qubits, all right? And they might be some distance in the lattice away from each other. So we excite one of them with some pi pulse. We then, and they're initially detuned. We then frequency tune for some time the 2 qubits into resonance with each other because of that, we have that ability. Again, these are frequency tunable qubits. We do that for some time tau, and then we detune, and then we measure both qubits, and we can look at the Rabi flopping between the 2 qubits. So this excitation was in qubit 1, and Rabi flops over the other qubit, depending on this time tau, and this coupling coefficient j. And we do that for every pair of qubits, right? And we can understand this matrix of hopping terms j by j. So here's a plot showing these measured as a function of the detuning from the band edge. This is from the lower band edge. So this green here, and this is the upper band edge. You can see this is the Jij. This is this hopping term for different I and J differences. So this is magnitude of I minus J. So this is the nearest neighbor term looks like this. It has a hopping term which decays relatively slowly as a function of the tuning because again it's just the nearest neighbors. And then I have I minus J to the 9. So this is this bottom curve here, which tails off very rapidly as a function of detuning because as I detune away from the band edge, my downstates become very close, and therefore, I don't expect interactions between qubits that are, the distance 9 away. And then we make the same measurements up here. So this is, a full characterization of this J as a function of the tuning in the system. And what you clearly see is that we do get long-range hopping. So we can measure this interaction well beyond just nearest neighbor, all the way across the full lattice of qubits in the system via these downstates. And it has, the detuning dependence that one would expect based upon the bound state, dependence on the detuning from the band edge. Then we can actually plot. We take this and want to know, what does this decay constant look like? Here I'm plotting the magnitude of the hopping term Jij to the hopping term for nearest neighbor as a function of the distance I minus J. And you can see that, you get this decay by more than an order of magnitude as a function. And in this case, at a frequency in the upper band edge that's at around 7.3, 5 gigahertz. You can see that I get this drop off for these, longer range interactions, which has, some sort of decay constant looks like, close to about 3 or 4 isotypes at that frequency. And I can map all of that out as a function of the tuning and fit that to a model. And we get very good correspondence between what we designed and what we're actually measuring for these hopping terms as a function of tuning and these, these downstate wave packet extents. So we have a very nice system with very controllable, tunable long-range hopping, but there's a few surprises, right? And we cannot understand these surprises from these simple two qubit experiments, and that's where things get a little more interesting. So, and this is probably, I think, the bulk of what is interesting about the work I'm going to present today. So, these sorts of 2 qubit measurements and single qubit measurements I show you allow you to understand your qubits very well in isolation. It allows you to understand how they're going to, these hopping terms in your Hamiltonian. But there's a few things in the Hamiltonian that these 2 qubit measurements cannot decipher. And you can only see if you do beyond 2 qubit experiments, so real many-body experiments. Right? So this is really now showing you the power of doing, that it's important, very important to do, not just to do individual, measurements of these quantum systems, but rather to study them in the many-body form. But that's really challenging. Trying to do tomography on a many-body state is really difficult. And so this was a collaboration with Soon-Won Choi and Daniel Mark at MIT to figure out ways in which we could estimate these many-body Hamiltonian parameters beyond just these, these 2 qubit single qubit measurements that I showed you. So how is that going to work? So let me walk you through that a little bit, and then I'll show you the data, which is really interesting. So basically, what we're going to do is we're going to do quench dynamics. We're going to excite into some, some excitation manifold of the system. So let's say we've got 10 qubits. We're going to, let's say, put 5 excitations into the system randomly amongst the qubits. We're going to bring them all into alignment, and then we're just going to let them interact through the many-body Hamiltonian. Right. So this state preparation, and then the quench is just letting them interact freely. Right. So they're in some excited state, and then we watch the dynamics. So we initialize each of the qubits into some initial z representing z equal 1 representing the excited state. We prepare each of the qubits into either ground or excited. We let them interact, and then we just do a global bit string measurement. We measure all the qubits. We measure whether they're in the excited state or the ground state. And you might think, okay, there's no way you're going to learn about the many-body Hamiltonian in this measure, right? Because you're just measuring in one particular basis. It's not going to tell you about the quantum phase of the wave function, things of this nature. And you shouldn't be able to get phase information about this. Turns out you can, if is chaotic enough, right? And it turns out that this system that we're exploring, because it has long-range interaction, goes from integrable, which is not chaotic, to ergodic, and which has quantum chaotic behavior. And the way to think about it, the reason you need something that's close to being chaotic is that once you do this quench, you want, at least locally, you want everything to scramble, any operators to get scrambled, okay, in some local region of the system, and you want that to happen quickly. And if that happens quickly, then when you do these measurements, you're basically randomizing, you're naturally randomizing your measurement basis in some way, to think about it, right? But you don't have to do it, you can just measure this one single basis. So the beauty of this is, I just excite the system and measure in one single basis, and I can learn with very high fidelity about this many-body Hamiltonian. So it requires, though, a little more analysis. So what you get out of these bit streams, if you repeat this many times over time tau, is you'll get a distribute for every one of these. You're going to get a histogram, right? For every one of the bit strings, you're going to, so there'll be some number of times that bit string came up, right? And then and that histogram will then give you probabilities for those bit strings. And it turns out that if you take these measured bit string probabilities, so it's not the bit strings themselves, it's actually the probabilities that they occur. And then you can actually theoretically, if you take an estimated, you take a Hamiltonian, if you think this is your system Hamiltonian, you can actually estimate what those theoretical bit strings are. And then if you do some sort of convolution of these measured bit strings and these theoretical bit strings, it turns out that this is an extremely sensitive measure of whether you have the right system Hamiltonian, right? So you have to multiply these measured bit string probabilities against the theoretical bit string probabilities in some special way. This is called this fidelity estimator. I'm not going to show you the formula, but it's relatively simple. And it turns out because because things get randomized like this, the way to think about it is that these bit string probabilities are like a fingerprint of the Hamiltonian, right? The actual fluctuations in these probabilities it's the fluctuations that matter, not the average. It turns out that there's an average value, but it's fluctuations around that average that is telling you about the behavior of the many-body Hamiltonian, and it's extremely sensitive. And I'll show you how that works on data. So this is a really nice way of measuring these many-body Hamiltonian parameters in a very efficient way. And it turns out for superconducting quantum circuits, it's extremely efficient. You can measure this in literally in tens of seconds, right? Just because you can do very rapid readout and you can do very rapid state rep. So you need to generate something like 1,000 samples, and that's enough at any one given tau to do a high fidelity measurement of what of your Hamiltonian. And so what we do is so let me show you some of this data. So this is the extended Bose-Hubbard model. And one thing that may not be so obvious is that if you're in the upper band gap, it turns out that the block wave of the metamaterial, right, has it's at the center of the Brillouin zone, right? This is the wave vector, the top band edge. So the bound states have the same phase every single unit cell. And what that means is that these hopping terms that we measured in magnitude, it turns out they all have the same phase, theoretically. But in the lower band gap, because you're at the edge of the Brillouin zone, and you have a pi phase shift there for the block mode. So the block mode is changing phase by pi every single unit cell. It turns out that these hopping terms, we have their magnitude from these 2-qubit measurements. It turns out their phase should theoretically be alternating. And that dramatically alters the many-body dynamics. So what we do is we do this quench dynamics for, let's say we excite into the n=5 manifold. Let it quench. We calculate as a function of tau this many-body fidelity based on the global bit string measurements. We find that, and again, we're in the lower band gap, we find that if we assume a Hamiltonian that has, or we don't, that alternating signs, we get some fidelity estimate that drops off. And this is dropping off because the system's losing coherence. So this is natural. If we assume all equal signs, we see that we get a lower fidelity. So it's not, we know that the many-body Hamiltonian is going to be much more likely to be with these alternating signs in the lower band gap. And then it turns out that if with alternating signs, this is using the magnitudes of the hopping terms measured from these 2 qubit measurements. And then if we just allow the system to optimize, we say, okay, we're just going to make those measurements, and then we're going to, move the parameters around and find an optimal value that optimizes the fidelity. You can see that's done here. At this point, we can see that we get an even better measure of the many-body fidelity. So this many-body characterization is extremely sensitive, even more sensitive than these 2 qubit measurements to these parameter values. So you can see just this small change. This was the value we measured from 2 qubit measurements, and then this is the value of the fidelity when we at the optimal value. And you can do that for every single parameter. So it's an extremely powerful way of actually getting out information with a many-body Hamiltonian that you can't get just from 2 qubit or single qubit measurements. And this is just showing you comparison between the 2 qubit measurements and the many-body, the 2 qubit measured parameters and the many-body optimized measured parameters. And we get very good correspondence except for 1 or 2 values. And it was those 1 or 2 values that made this big jump in the fidelity. Okay, one of the other things we can do with this many-body characterization. Here's another quench dynamics plot. One wants to think about this more like a random walk. So what we do is we excite 2 qubits in the center of our array, qubit 5 and 6, at time tau, and then we let it quench. And so these are just going to be 2 random walkers on the lattice. And because they're bosons, we expect them to separate out in time, turns out. And so this is the experiment. You can see it starts here, and then it just, you get basically a mess after that. You have, some sort of really spotty probability of finding the excitations on any part of the lattice. Theoretically, that's basically what you expect for a system that has chaos, right? But if it's an integrable system, you can see these revivals. And so that's what you'd get if we had nearest-neighbor interactions, not long-range interactions in the system. And this is just showing you a cut. We can look at the population distribution of these random walkers, but now we can look at correlations of these random walkers, these 2 random walkers. And so these are the 2-site correlations. And so here's, and you can see this is, again, experiment theory. They look pretty similar. And what you can see, there's more in this 2-site correlators for the integrable theory. You see more of the spread, less of the spread in these 2-site correlations. And this is directly related to those bit string probabilities that I'm telling you about. One way to think about this is that these are speckle patterns in these 2-site correlators, right? Very much like laser speckle. And it's the randomness in that speckle that we're actually using to make this fidelity estimator, right? This is another way of viewing this. So, but if I look at these 2-site correlators, honestly, this isn't going to tell me much about, the fidelity of the Hamiltonian. So, but I can actually quantitatively do those bit string analyses and turn these speckle patterns into something that's much more, meaningful and quantitative. I can see that there's differences between these speckle patterns between experiment theory and then the integrable theory, but I couldn't quantify it unless I use these bit string analyses. And so here's just showing you that again. This is for where I have long-range interactions. This is a function of time. This is showing you the second moment of the bit string. So what's the variance in this bit string distribution? And it turns out that there's an ergodic limit that's set for chaotic systems, which goes like 2/d, the dimension of the Hilbert space. And that ergodic limit, you can see is satisfied at least for moderate time scale. So you see this initial quench, this fast quench. This is on a logarithmic time scale. And you see that the theory and the experiment, theory being this long range, many body Hamiltonian that we, with parameters we found from the optimized many body characterization, we see that that quenches, and again, this is on this second moment is on a logarithm scale. So there's a big difference between this integrable theory, which shows a lot of oscillations, and it never really settles down to one that's ergodic, which settles down to this ergodic limit. And then you can see that the experiment actually has a few other features, like at long time it starts to decay even further, and it turns out that this is the completely random limit here that it's decaying to because we're losing coherence in the system. So, what do these distributions of these different time scales of these bit strings look like? So at early times, right, we have very high probability states, bit strings, because the system hasn't, thermalized it, hasn't randomized it. So the distribution looks almost, it looks, like with very high probability, you have these states, and it's not very uniform. In these times where it's actually thermalized, where it's actually, it's actually randomized, you get what's called a Porter-Thomas distribution. So this is the distribution you get there for the probabilities of those bit strings. And it's the deviation or around this Porter-Thomas distribution that is this fidelity that I was talking about. That's how you measure it. And at these long times, as I mentioned, it goes through almost a completely random system where every bit string has a probability of 1 over d. So you can see it goes from Porter-Thomas to something that's much more localized, with where everything has a mean value, every bit string has a value close to 1 over d. Okay, so for me, this is, again, what I really like about this is something that would have been really hard to measure if we hadn't used these techniques. It also shows you that we can't think about even these circuits that have modest numbers of qubits. We cannot think about them in the normal ways we think about them. We can't measure them in the normal ways that we want to measure them. We really have to treat them as many body systems. And we have a lot of tools that we don't have in like normal, non-synthetic, let's say more natural quantum systems. We have a lot of tools at our disposal, and people are developing these new tools every day, right? But they're very powerful. And it's the way we're going to understand how to better manipulate and control these larger, complex many body particles. This is just an example of it. So outlook. Okay, what do we want to do with this, right? So it's pretty cool. We can measure we've been able to make this circuit has this, chaotic, quantum dynamics, which is really interesting. It has these tunable long-range interactions. But so what, right? We can develop these tools. So what are the things we want to do with it? So one thing is, it turns out this extended Bose-Hubbard model with these alternating signs has really interesting phases. So this lower band gap, it turns out, where you have alternating coupling between the different states, but the coupling sign alternates and is long range, but the anharmonicity is pretty constant as a function of the tuning. And it turns out that this favors, what it does is it frustrates the superfluid phase. And it favors a mod insulator phase. So it stabilizes the mod insulator phase over a much larger ratio of tunneling to on-site potential than you would get for a normal Bose-Hubbard model. Whereas in the upper band gap, you have the opposite. You have a rapidly changing anharmonicity that can actually get very small. And you don't get this frustration due to the sign of the hopping, and so you tend to form the superfluid phase. And this just shows you that this is sort of a phase diagram, where this is the chemical potential. This is sort of like the particle number that I'm putting inside the system. This is the ratio of the hopping to the on-site potential. And you can see that I have this mod insulator phase inside of here. This is for nearest neighbor interactions, and then this is a critical point here where I have this transition to a superfluid phase. If I go to an upper band gap, I can see a dramatic reduction in that region, which is mod insulator, because it favors the superfluid, and then I have this very extended mod insulator phase if I'm in the lower band gap. So we'd like to study this phase more carefully and look at these parameters. We think that's interesting. We can also go beyond just simple couplings, and this gets to some of the work that are done here at Stanford in terms of how you can use different modulation techniques to generate arbitrary graphs of couplings between atoms and cavities. We can play the same game in this sort of system, where one uses parametric modulation to create various sidebands of each qubit that then each have their own bound state and own detuning and thus own interaction strength. And you can generate really, in this case, we can generate different power law profiles for the coupling, not just exponential drop off of the coupling. You can also generate these interesting graphs that people are able to do in cavities with atoms. You can also do interesting dispersion engineering beyond, just the upper band gap, pass band, lower band gap. It turns out you can actually add topology into the metamaterial waveguide, and this can give rise to really interesting spin physics in these systems as well. We can also go beyond one dimension. So we can go to two-dimensional circuits with arrays of metamaterials along rows and along columns, and we can do that, and that gives us a two-dimensional region of interaction within the lattice, as opposed to these one-dimensional systems. And that can be in this, very nice technology that's been developed that allows you to flip two different chips together and allows you to do this sort of wiring with two-dimensional arrays of metamaterials. That can allow you to do all sorts of interesting 2D lattices, ones with flat bands. You can, there's a lot of different exotic things that can be done once you go to 2D. 2D is much more interesting in this case than in 1D in most cases. I already mentioned that one can create non-local gates for gate-based quantum computing. So this is another way that we'll modify the sorts of systems we're making and study them for actual gate-based quantum computers. And here the idea is that there's a fundamental trade-off in quantum error correction in 2D lattices when you have local interactions. It turns out that the number of logical qubits you can generate and the code distance is related in this way to the number of physical qubits. And so if you have non-local interactions, you can actually get more logical qubits or a larger code distance for the same number of physical qubits. And that's very important for reducing the overhead in quantum error correction. And it's fundamental. And so we can do that by adding in, we can actually make a gate-based version of what I just showed you by adding in tunable couplers that allow us to tune the interactions between, turn on and off these interactions between the qubits and each of the resonators. Okay, so I'm going to end there. I just want to point out the students that really did all of this work. They did everything from the design of the microchip to a lot of the condensed matter physics modeling to the actual measurements and analysis. So Sherry Zhang is a PhD student in my group, and she worked along with Ujang Kim, who was a PhD student in my group and now a postdoc. So they were the two that did all of this whole experiment together. And as I mentioned, theory collaborators were Daniel Mark and Soo-Won Choi at MIT. They were predominantly the ones that developed this many-body fidelity measurement. And then in terms of doing the waveguide QED, we worked with Miguel and Alejandro, and with Derek Chang and Ana Garcia. So they were very critical to some of the early work we did with these systems. So, thank you very much, and happy to take any questions.
The first few questions are from students.
Thank you for your enjoyable talk. Very beautiful design of quantum hardware. But something that is really bothering me is that in the quantum tomography side, the way that you did the quantum tomography was by evolving the Hamiltonian in a classical computer. So the reason that we build this quantum simulation is to do this stuff on the chip. So it's a little bit like the chicken and egg situation for me, like how to
I think that exactly. So the tools that I showed you are not going to work as soon as the systems you can't simulate them on a classical computer, right? It requires us to simulate the system and then do this analysis. I think, at least for the time being, that's the way we can develop tools, right? Using a smaller system. It's still, what will be challenging is as system size effects become really important, we won't be able to model those sorts of effects, right? So that'll be a big challenge. So, this works well if you're going to limit yourself to certain sizes and you're not, let's say, trying to extrapolate out to large system sizes and try to understand the physics there. Right? So those will have to be different tools and different methods. This is just one of them. But I still think that what I really like about this, even though you can model it, it's just it's such a simple, from an experimental standpoint, this would have been really hard if we done it any other way. So, but I agree with you. I think that ultimately this is just one tool, and it's going to have, that's going to be in a toolkit that we develop over time. we're going to need better tools to develop larger systems as well that don't rely on us to classify people. May not be possible.
So we have a question on Zoom from Ling Ling Tan. Could you elaborate on the tunable mechanism of coupling? How much time does it take to stabilize once you reconfigure all the couplings?
Okay, so right now, in terms of how we change the couplings, it takes about 1 or 2 nanoseconds to tune our qubits into the appropriate frequency from, let's say, their park frequency, align them, and then do the quench. So it's about a few nanoseconds, and we have to do some special, pulse distortion or pre-distortion to get rid of any ringing and things like this in the system. So there's a lot of calibration of that tuning, but you can do it over a few nanoseconds. I'll go here first, and I'll get you that.
You showed some really nice plots on describing like the chaotic behavior of your system. Is there a system parameter you can tune that changes it like from chaotic to integrable?
Yeah, let me show you that. I didn't use your backup slides, so let me find that for you. Yeah, you can. There is, and I didn't show that data, but don't behind it. I'll just tell you. Here it is. Okay, so you see here, what we can. This is. Let me actually go through this slide. So we can also measure this transition between integrable and chaotic behavior using this bit string analysis as well. So what we're doing here is we're moving the detuning from where we have more local interactions, so we're just weakly breaking the integrability, to much longer range interaction as we get closer to the band edge, where we're strongly breaking it. And you can see the transition from integrability to non-integrability in this bit string system. So you see here's the integral model. Again, it's a log scale, so keep that in mind. You see this quench, and then you just see it keep oscillating. It just doesn't settle down. But that's classic integral system. And this is the second moment of the bit string, so with the distribution. We then, and then here's this ergodic limit that I was talking about. It should settle down to if it's chaotic, right? So we should get some emergence of these universal statistics in the bit string. So, and again, this is like just focus on this first initial recovery, which is unnatural for a chaotic system, but for an integral system, one would expect. So we can see if we're here in frequency, very far tuned from the band edge, where we have almost nearest neighbor interactions. We see this recovery, and we see, so we do see this sort of integral behavior in terms of this the second moment. We then get closer to the band edge, and we start to see that fade, and then it just it gets really close to the ergodic limit. So that's that transition.
Thank you.
Yeah, I'll live here, and then I'll go to John.
Thanks for the great talk. I had a question about if there are any benefits basically to operating in the upper band gap versus the lower band gap, or if it's problem specific.
I think that, okay, there's technical reasons why the upper band gap is hard to work with. I would say that, I mean, if you want to, I think comparing the two phases is interesting, so we would want to do that experiment. The problem with the upper band gap is that you're at higher frequency, and your anharmonicity, like as you bring the qubit, let's see, I can show this here. So there's one a challenge here that is maybe not so obvious. And the lower band gap is just easier to deal with. And this is, again, a little bit technical, but I'll show it anyway. So if I run the upper band gap, let's say this is the 0-1 transition of my qubit, right? Trans 1s have a negative anharmonicity. So their 1-2 transition is lower in frequency. So it's going to be closer to the band edge. So as I bring my qubit close to the band edge from the upper band gap, I see a dramatic change in my anharmonicity because this 1-2 transition is starting to hybridize with the band edge. Right, and that this dramatic change in harmonicity is something, okay, it's interesting, but this hybridization with this band edge state is something that can cause the system to decohere more quickly. Whereas in the lower band gap, because the 1-2 transition is below in frequency and I'm coming from below, then I don't see such a strong change in the harmonicity in the lower band gap. So it's another reason to use it. So I think you can use it. There's benefits to it. It's interesting to see this, like to go into the switch phase. It's really easy to go into the switch phase because you can turn off this on-site potential. You may want to study that. But you do start to hybridize, and technically it's just a little more challenging. I think it becomes a little more lossy.
Thank you.
So you have this long-range tunneling term.
Yeah.
That you've engineered. Is it possible? I mean, the Bonnier functions are delocalized. Shouldn't there be a long-range density interaction as well?
Yeah.
So is that apparent in the? I mean, okay. So I guess one question is the numerics that you showed.
Yeah.
Was that numerics in an effective model, or was that numerics in the underlying?
That was numerics in the underlying model.
I see. So it probably has those.
Yeah.
Those terms.
That's what terms of it. Yeah.
I see. Is there a sense of how big they are?
It's a good question. I'd have to go back and look at it. I can't recall, but yeah, maybe.
The reason I ask is I think that Bose-Hubbard phase diagram actually changes substantially if you have finite range density.
Yes. I think yeah. So that was the MRG analysis that we're doing.
In the underlying model or in the effective?
I think it was in the underlying model.
Okay,
but
great.
I
So-
didn't convert it.
Got it.
Yeah. So it still even with that, I don't know how much it changes that phase diagram, but it's still what I showed you.
It just seems like at some point there should be like fractional filling
Uh-huh.
phases if you have density.
Oh, yeah, I mean, I'm just showing you, yeah, exactly, yeah, you should see those as well. This was specifically to this, unit filled system. Yeah, I'm not looking at any of those other states. So this is specific to the unit filled, it's gap, right? So I'm just looking at that.
An extension of this hybridization question, why did the data seem to fit so much better in the upper band gap for that two-body system, the coupling, than it did for the lower band gap? Like it seemed to diverge pretty quickly.
Okay, let me go to that.
And if there is this hybridization, it is tricky to work with. That's kind of surprising.
Right, you would expect the opposite. I can tell you what's tricky about fitting that data, which is not related to this hybridization, but it's related to something else. And it gets into this sort of, what model you're using, sort of question that John was asking. Let's see. Maybe it's right. So it turns out that if you want to just model the circuit, take the circuit and then generate a Hamiltonian from it, it turns out that you cannot assume this simple model of either resonators, LC resonators coupled capacitively to each other in series. It turns out that charge and currents are non-local in this picture. So you actually have long range coupling in that metamaterial. So just describing the metamaterial for a moment, like what the behavior of the metamaterial is. So the metamaterial is not just a series of resonators that are coupled serially together. It turns out that that's too simple a picture. You actually have long range coupling amongst those cavities. And again, I'm not modeling the whole system now, I'm just modeling the metamaterial as a bus. And you actually have to take into account a larger capacitance matrix that talks about the coupling across all the sites. And when you do that, it's just more complicated, and that's what you're trying to fit to when you try to predict the size of these bound states, right, and their behavior. And it's probably due to the fact that we have some parasitic, couplings that we're not capturing in our simple capacitance matrix. So that makes sense. So I print a circuit, right? I try to estimate the lumped elements, but it's not a good estimate of the actual circuit itself because I'm going to have long range I'm going to have capacitance across you know, that I'm not necessarily capturing in a simple lump element model. And that's why I see these differences. And it's particularly worse in the lower band edge. Yeah, these effects. So we try to capture those things, but you know, you can only do that so well, like you know, in terms of trying to write a lumped element model of what the actual full, you know, what that thing printed on the surface of your silicon chip actually is in terms of capacitors and inductors.
Thank you.
Have you thought about how to stabilize some of those spaces?
We have, but we haven't actually we're just starting to do the experiment. I'm not sure how effective it will be. Yeah, so I can't say that I know I have a really good way to do it. We have some thoughts on how to do it, but that's another big challenge. I mean, those are things that you know you studied in particular, and I think that's enough. You know, that's sort of, I would say, like being able to access these different states and phases is something that we haven't done yet. We've just done simple quench dynamics. But if we wanted to do more exotic, stabilize more exotic states in the system or phases, then there's, you know, again, another series of tools you need to build up and techniques.
But you could potentially use your photonic crystal to
Absolutely. Absolutely, exactly. So that's one of the tricks, is that metamaterial waveguide is an amazing, system to use just to get rid of entropy in the system. And we use that actually to do reset of our qubits. When we read them out, we can do reset in about 20 nanoseconds for all the qubits. So extremely fast reset with very high, like sub tenths of a percent. And then it's unconditional reset. So there's a lot of little technical things with this metamaterial that make it amazing to work with. So, and again, we do multiplex readout. We do all the 10 qubit readout simultaneously. And we have a fidelity of over 98.5% for individual qubits, and the total 10 qubit string fidelity is over 70%. That's not easy to do. Mux at 10 qubits, and then we're able to do this reset. So there's just really nice things that this metamaterial allows you. Again, very technical.
I have to ask one more question about that. How sensitive is this stuff to read out errors? The tomography stuff.
Not so sensitive. I mean, we had to. I should say, at the level we were doing it, you know, again, we have our 10 qubit readout fidelity is around 70%. All I can say is that it's not sensitive at that level. That's good enough.
And then what about decoherence?
Yeah, I mean,
That's in the model.
Yeah, it's in the model. Yeah.
Can I ask a question?
Yeah.
I was actually surprised with what you showed where the amorphicity goes down for the upper gap. Kind of naively would have expected if you put the 1-2 transition into the gap, you broaden it, you know, you sort of teaching it frequency space even farther.
But it tends to push it up, right? And then it gets closer to it pushes it. So if you're coming down in frequency,
right,
it tends to push it away from the band edge, and therefore it's like closer to the 1-0 transitions.
So does that curve go up again ever? Like, is it?
Yeah, when you pass through it.
Yeah.
Yeah, it does funky things. So I don't. Yeah, and once you actually fully hybridize, actually, there's no longer bound states. So they become unbounded.
Right.
So that and so we only showed it up to the. That's why we don't go to 0 to tuning. If you do that, then the state becomes leaky. So you don't have a bound state anymore because of this. Because of your second excited state hybridizing goes on. So there's some criteria for it, I don't recall, but like if you get, you know, a certain distance and the strength, coupling strength is a certain amount, you can show that it becomes unbounded. Yeah. So we only go so far, and then we go farther. Yeah, we weren't actually anticipating that something we ran into. They would like come unbounded.
Any other questions? Okay, so in that case,